So, welcome to a new Interalagi conference series. Today, we have a great talk. The doctora Bea Gallardo-Lacourt. Uh, sorry. Um, with the talk titled Steve and Beyond Unlocking the Secrets of Solar Aurora Phenomena. Uh, Doctora Bea Gallardo-Lacourt is a very famous researcher in Latin America. So I'm sure many people know about her works. A little resume about the biography de Bea. Doctora Bea Gallardo-Lacourt is a researcher at NASA Goddard Space Flight Center and the Catholic University of America. She specializes in magnetosphere and ionosphere coupling and the dynamics of aurora and subaurora regions. Original from Chile, she earned her PhD in 2016 from the University of California, Los Angeles, UCLA. And Bea serves as a geospace editor for AGU Books, is the international secretary of ALAGE, a former chair and current member of the EGU SPA Early Career Committee, and an organizer of the STEVE workshop, among numerous other professional and volunteer service roles. She is actively involved in several NASA missions, including GDC, Cinema, and Punch. So, Bea, let's go.
Thank you so much, Carlos, for the introduction. If anyone wants to talk to me about any of the other things that I'm not mentioning today, feel free to send me an email. I'm very, very happy to talk to you. So thank you so much for the invitation to give this talk today. It's really nice to be able to give a talk to the Interalagi students. And I'm very, very excited. So if you don't get a chance to ask your question today because you're too shy or because you need to think a bit about it, email me, contact me. I'm very friendly. I speak Spanish too. So reach out to me in any language that you want. So when I started working on this talk, I wanted to make it in a way that you guys will get something out of it. So I'm not trying to advertise all the 15 papers that we have published, but I want to make a case for at least 2 of the most important characteristics that Steve had. And for that, I need to teach you a little bit about the aurora, about where the subauroral region is, about the phenomena that we see there, and about what we see on Steve and what we don't see for it. So when I did this talk, I realized that what I'm going to show you today is actually kind of the tip of the iceberg. Notice that the iceberg is purple because of Steve. So today we're going to just see what is above the sea surface, but everything that is below, it's something that we can talk about it in another setting because it will take me about 2 hours to tell you everything I know about Steve. So as usual, one of the best places to start is perhaps to think about our system. And a great place to start is something that you probably know, space weather, and why space weather is so important. So the way we usually define space weather is when we talk about the conditions not only in the sun and in the solar wind. The solar wind is that mix of magnetic field from the sun and charged particles that travel through the interplanetary medium and affect planets. One of those planets, of course, is Earth. It changes the magnetic field of the Earth that we know as the magnetosphere. It affects also the ionosphere and the thermosphere system, so our upper atmosphere. And these solar wind conditions can also influence the performance and reliability of our instruments, spaceborne, and the ones that we have on Earth, as well as impact human health and life. One of the best ways to observe the effects of space weather is perhaps what we're seeing right there, the aurora. The aurora is something that will inform us very quickly how is space weather behaving. When we talk about the aurora, it's very important that you understand how the aurora is produced. And the mechanism is relatively simple. As you can see from my first bullet point, we have known how the aurora is produced for already 100 years, almost 100 years. So there was this beautiful paper that if you have a chance to read, it's like a real letter from the 1932 from Lars Vegard. It's one of the old Nature papers in which they explain how the aurora is produced. So bear with me while I show you a funny animation. So if we are looking at Earth, we know that closer to Earth, the atmosphere is very dense. So the closer we are, the more particles we have, the more neutral particles we're going to have. We also know that the Earth has a magnetic field, the magnetosphere, and these magnetic field lines are connected to Earth. They close inside of Earth. And then we have particles that move along those magnetic field lines. And when they're moving along those magnetic field lines, sometimes they can collide with the neutrals in the atmosphere. And when these particles collide with the neutrals, if this is an electron that is moving along the magnetic field line, collides with the neutral end up energized. And if you have several neutrals, instead of having one particle, you have several, you have something that will resemble an arc. So when we take that electron moving along that magnetic field line, is what we're going to call the electron aurora. The collision between the electrons and the neutrals is known as the electron aurora. And the most typical emission lines are the green and the red line emissions that are produced by the de-excitation of atomic oxygen. And we also have the blue and the purple that are produced by the de-excitation of molecular nitrogen. If instead of being an electron moving along the magnetic field line, now we have a proton, the proton does something different. Instead of energizing the neutral, the proton is going to go charge exchange collision. So it's going to collide, and it's going to be the proton that ends up energized. The proton typically emits in the two Balmer emission lines, the H alpha and the H beta, and the H beta is what we measure on Earth. If you have never seen the aurora, or if you have seen the aurora, I can guarantee to you that what you are seeing, or you will see, is the electron aurora. The proton aurora is not visible by the naked eye. We need a special instrument to measure protons, and that is something extremely relevant for the talk today. Very important too is that we have emission lines. So for example, when we look at how is the emission of the oxygen that we were talking, those emission lines are discrete emission lines. It's not in the full spectrum. So what you are seeing here is brightness or luminosity as a function of wavelength. And you can see that for the oxygen is not a full continuum emission. The oxygen has an emission in the 3000 Armstrong, one that is the green line in the 5577 Armstrong, and then the 6300 Armstrong. That is the most common one that I was talking earlier. So remember that. Also remember that the aurora is not a process that is exclusive for the Earth. There are other planets that also have magnetospheres where we have observed the aurora. And I'm giving you two examples here that have been captured by NASA satellites. We have the aurora in Jupiter, which is very majestic because the magnetic field in Jupiter is so strong. And we also have the aurora in Saturn that is also very, very impressive. So on Earth, the aurora is extremely interesting. And you have probably heard the term the aurora, the auroral oval. And it's because when we're looking the polar regions of the Earth, like we are doing right now from above, we can see that the aurora occurs in something that it looks like a ring or an oval. And if the day side is over here where the sun is, we also say this region over here is the night side. One thing that is super important is that we have two ovals, right? I'm showing you the northern hemisphere right now, but we also know that the same is observed in the southern hemisphere. So in the northern hemisphere, we have the aurora borealis, and in the southern hemisphere, we have the aurora australis. And as I was telling you a second ago, we have the day side, and then we have the night side in this region. So imagine it is like a clock. And we usually call this clock, this imaginary clock that we have to put on top, the magnetic local time, where noon is going to be towards the sun, so the 12, is going to be towards the sun. Sorry, I had to invert this clock so it will be the correct location, and then midnight will be on the other sense of the sun. This area is the dusk area, the pre-midnight sector. See that this is 23 MLT, 22 MLT, and this is the post-midnight sector. And the phenomena that I'm going to be talking today occurs in what is called the pre-midnight sector, in this area over here. And while within the auroral oval, we have so many very dynamic optical structures, below the auroral oval, it's not known for being that incredibly bright and incredibly structured, except for the things that I'm going to show you today. So I'm going to focus on what is called the subauroral region. That is a region below the auroral oval in latitude, as you can see here, and in the pre-midnight sector. So right before the magnetic midnight, when we have a lot of auroral activity. So what is happening in this subauroral region? The best way for us to look at the subauroral region in the past, and even now, but probably one of the best instruments that we had, was what is called an incoherent scatter radar. And there is one that probably most of you know that is located in Jicamarca. It's a very famous, very productive, and as a scientific instrument, it's a brilliant scientific instrument. And a similar one is located in the Northern Hemisphere at Millstone Hill radar, and that's the radar that you are seeing here. The two parameters that we're observing here are, in the first panel is velocity, and in the second panel is electron density. Westward is going to be positive in this case. So if I go back a second, if we're looking here, this is the east coast of the US, this is the west coast of the US. Westward is going to be from midnight towards the pre-midnight sector, towards what we call the sun, like around. Imagine the plasma is moving around in this line. So that is going to be westward, towards the pre-midnight sector. And those are going to be positive values in this case. And then we have electron density, both of the parameters as a function of latitude, with latitude increasing towards your right. So if we start moving from high latitudes towards low latitude, what we see in the velocity is all the fast-moving structures within the auroral oval, or all those dynamic arcs that are being captured by the radar. And then we have what is called the auroral equatorward boundary. And this boundary is not set arbitrarily. We look at particle data, particle precipitation data from satellite data. In this case, this is coming from the MSP satellite, and we find where that precipitation of electrons ends in latitude. And that is exactly this red line. Very interesting, right below that equatorward boundary, we have a region of fast flows that is relatively wide. This is about 5 degrees wide sometimes. And this region of fast flows is co-located with a region of low electron density, so what we call the plasma trough. Very interesting when people started looking at all these measurements from satellite, from ground-based instruments like Millstone Hill radar, they started calling it different things. And in 2002, John Foster organized a meeting in Millstone Hill Observatory, and all of them got together and they decided to unify the term. So for everything that they were seeing, instead of calling it, as I put here, polarization jets, subauroral ion drift, they decided to call it subauroral polarization streams, or SAPs. And it takes everything that is in the spectrum of these. SAPs is usually wider flows, but sometimes we also observe these very narrow flows at the top of this enhancement that are usually of 1 or 2 kilometers per second that we call subauroral ion drift, and those are very, very fast. So today I'm going to center around those SAID, subauroral ion drift, that are part of these SAPs. It's a subset of SAPs. So how are these fast flows that we see in the subauroral region being formed? And there are at least a couple of different mechanisms, but this is one of the most accepted ones. And this was introduced by Phil Anderson in his 1991 and 1993 paper. This diagram over here is actually the schematic explanation of Phil's theory, but I decided to do something that is a little bit more friendly for 2025. Another thing to have in mind is the current system. So I want you to remember that in 1978, Ijima and Potemra, these two scientists, started looking at what is called field-aligned currents, currents that go from the magnetosphere into the ionosphere. Those currents sometimes are called Birkeland currents, and that is because there was a Norwegian scientist that was studying these field-aligned currents. He proposed that there were currents that connected Earth's atmosphere with space. And actually, this was at the beginning of the 1900s. And when Christian Birkeland proposed this theory, people were thinking that he was crazy. It's actually a sad story because he was so enamored by the idea of studying the aurora that he was working with something that is called a telera. I think it's telera, but it's mercury. Mercury is generating all the atmosphere, all the aurora. So the theory is that he got poisoned by mercury. So a lot of the scientists did not believe that he was in his right mind to propose that there were currents connecting Earth's atmosphere with space. And about 60 years later, satellites actually corroborated that Birkeland was correct. So many of us, in honor of Birkeland, sometimes we call it the Birkeland current. And when Ijima and Potemra in the 70s, imagine 70 years later after Birkeland proposed that these currents exist, did a statistical study taking one of the satellites that we had at that time and started looking at what the currents, the field-aligned currents, look like in around the times of substorms. So I want you to focus, again, we have the clock, so we know that the sun is on this side, this is magnetic midnight. I want you to focus on the pre-midnight sector. And on the pre-midnight sector, we have basically two main currents. The current in black, I know this is very small, is a current into the ionosphere. This is a region 1 field-aligned current, that's what we call it. And then the current at higher latitudes is away from the ionosphere. So it's going to be from the ionosphere into the magnetosphere. And that's a region 2 field-aligned current. Remember that because that's important for what I'm going to explain you in a second. So for simplicity, let's say we are in the northern hemisphere and we are looking at the aurora. This is the equator boundary. So the auroral oval is dancing up here. The subaraural region is right here. North is towards the top of the page. And we know that in the northern hemisphere, the magnetic field lines go into the Earth. So in this case, it's going to be into the page. If that's magnetic midnight, we are in the pre-midnight sector. So in the pre-midnight sector, we know that two current systems exist in the more global sense. We have a downward field-aligned current, a current into the ionosphere, and then at higher latitudes, like you are seeing here statistically, we have an upward field-aligned current from the ionosphere into the magnetosphere. We know that if we have currents in and out of the ionosphere, these currents need to close because we have to have current continuity. So we have to have a current that if we have a current into the page and away from the page, we have to have a current that is pointing up, a current that is pointing forward. And we know this as a forward-directed Pedersen current. And you know from electrodynamics that if you have a current, you have to have an electric field. And that electric field has the same direction of that current, a power-directed electric field. So now you know that you have an electric field in this direction, you have a magnetic field into the page, and if you play a little bit with the right-hand rule, you know that you have to have a flow that is westward. And that is how those westward flows in the subaraural region are being created. I highly, highly encourage you to play a little bit with this so you will get the signs correct and everything correct. So do it. So how do we study the subaraural region and space weather in general? I'm one of these people that when you have a problem, I toss everything that we know at it and everything that we have at it. And when it comes to space physics, we basically have two types of instruments for people that work in experimental type of setups. We have the space-based instruments that are usually on board of satellites. And also we have the ground-based instruments that we have different kinds. For the space-based instruments, the satellites, we know that we have instruments or satellites in different orbit exploring different regions of not only of the magnetosphere and the ionosphere, but the whole heliosphere. And these satellites allow us to explore different areas and different physics of our system. So I usually use as an example Themis that is in the magnetotail and is able to tell us how the dynamic magnetotail evolved and what are the main processes that are taking place. Similar in the ground-based instruments, we have a large variety. Here I'm showing you all sky cameras. This is particularly the Themis all sky cameras that are white light cameras. These have just been color-coded in green because we usually say that whatever we see in the white light is mainly green light emission. So that's why people sometimes color them in green. And they help us understand the dynamic of the aurora. We have magnetic field variations that can be measured with magnetometers. We have radars, like I was showing you, the incoherent scatter radars, but we also have coherent scatter radars. So we have used a bit of everything to study the subaurora region and to study what I'm going to introduce in a second, Steve. So what is Steve? And pay attention here because this is Steve small letters. It's going to become capital letters in a second. So Steve is actually a phenomenon that was discovered by citizen scientists. And it was a very well-known phenomenon for the photographers, but it was completely new for the scientific community. And Steve in this video is this white purplish arc that is moving in the video. And sometimes we observe Steve together with this green finger-like structure that moved together with it. This observation happened right below the auroral oval. It wasn't within the oval or anything. And it was very particularly structured. It was very narrow. The colors didn't resemble the aurora. The dynamics do not resemble the aurora. So when the photographers got together with the scientists, the photographers kept calling Steve the proton aurora. And now you know something about the proton aurora. The proton aurora needs a special instrument to be observed. It needs an instrument that is called a meridian scanning photometer measured in a particular wavelength. So we knew that whatever they were seeing with the naked eye and also with the cameras couldn't be the proton aurora. So the scientists asked the photographers to select a name that will not carry any physical meaning. So we will not have to, in the future, correct not only the scientists, but also the community. So they selected a name that is called Steve because of this movie Over the Hedge, in which the animals were so afraid of the human noises that they put a familiar name for them not to be scared. So they call it Steve. So that's why our Steve is called Steve. One of the things that I always say to the students is, I can imagine that many of you doing research sometimes feel like a lot of the things and a lot of the questions that you have asked yourself have been already answered, or someone has an intuition, or someone knows what's happening. And that makes it sometimes very challenging, very interesting, but it gives the idea that everything is known. And to me, when I stumbled upon Steve was completely new. I was still a student when I started working on Steve. And this gave us the opportunity of ask questions in a very fundamental way and maybe do research and answer questions that someone will say, oh, but that's so simple. But even if it is a simple analysis, it's something that we don't know. So we could not only ask simple questions and get brilliant answers, but use simple tools to really get deep inside of what was going on with the phenomena. So we did write this paper that is a short EOS paper that is called How Did We Miss This? How did we miss Steve if it was so obvious in the data? And I have my own theories that we can talk about it at some point. So how does Steve look? And these are my two favorite images of Steve. So what you have here is Steve is over here, and then you have a region of diffuse aurora right forward of Steve, right at higher latitude. If we look at it in a more extended way, we have north is in this direction of pole, where it's going to be to your right. We have the region of the discrete aurora. The discrete aurora are usually those very well-defined arcs that you have in your mind for when you think about the aurora. And then equatorward of that, we have a region of the diffuse aurora that is a slightly less structured, more dim type of aurora, more diffuse aurora, therefore the name. And right at the equatorward edge of the diffuse aurora, we observe Steve. So these two images were taken by citizen scientists, by photographers, but we needed our scientific instruments to be able to capture Steve to understand really what was going on. And that happened almost 10 years ago. I cannot believe that this is almost 10 years ago. In 2016, July 25, where we have one of our all-sky cameras. This is a camera that measures in the red line emission, in the 6300 nanometer emission. And this is in North America. This is actually in Canada. And what you are seeing in the middle of the camera is Steve. The Steve observation was also corroborated with one of the photographers' data. And then right at the time of Steve, we had one of the ESA swarm satellite crossing right through the structure. And that was extremely useful. So that data is summarized in this stack plot. The first panel is going to be luminosity as a function of latitude and time. Then we have that westward flow velocity, that ion westward flow velocity. Westward is going to be negative in this case. We have magnetic field perturbation. So these 4 panels are from swarm satellite, and the first panel is from the optical data. We have electron temperature and electron density. So when we look at the high luminosity for Steve, we realize that that was co-located with extremely fast moving ions. This is about almost 6 kilometers per second in a region of a small magnetic field perturbation with very high electron temperature and very low electron density. This type of signature, right below the auroral oval, very fast flows in a region of low electron density, is something that we know, right? That is a subauroral ion drift. We were observing a subauroral ion drift, but not any subauroral ion drift. When we were looking at this plot earlier, you heard me saying that typical subauroral ion drifts are about 1 or 2 kilometers per second. If you look at the flows here, this is almost 6 kilometers per second. This is extremely fast. So this was extremely fast, but not only that, the temperatures, the electron temperatures that we were seeing were very, very high. This is about 6,000 Kelvin. These are not temperatures that are normal or very common in the Earth atmosphere. To give you an idea, this is what we measure in the sun's surface, very hot. And also in a region of very low electron density. So this is very few particles that are getting very hot and are moving really fast. When we look at the magnetic field perturbation, this was interesting because when we talk about particle precipitation, when the electrons go from the magnetosphere into the ionosphere, we know that by definition, the currents go in the other direction. So for electron precipitation, we have what is called an upward field aligned current, a current that goes in the opposite direction of the electron motion. So that upward field aligned current is going to go from the ionosphere to the magnetosphere. This magnetic field perturbation actually led to a downward field aligned current, which will indicate upward going electrons. So this gave us a hint that maybe Steve, what we were observing for Steve, was not produced by particle precipitation. And I'll show you that in a second. So because of the characteristics of the SAID, then Steve became a backronym, something that we define kind of backwards. And right now, Steve stands for Strong Thermal Emission Velocity Enhancement. So as good scientists, we needed to know that this was not one case where we had a subauroral ion drift associated with something optical. It was the very first time that a subauroral ion drift has been related to something in the optical. So for that, we did a full statistical analysis with all the all-sky imagers. And although these were very few events, we found 8 events that had conjunctions with this ESA swarm satellite. And for those 8 events, the characteristics were very, very consistent. We consistently observe extremely low plasma density, high electron temperatures, and high ion flow velocities. When we compare it with regular SAIDs, and here I'm just showing you the electron temperature as a function of number of events. So in purple is going to be the regular SAIDs, and in orange is going to be Steve. And you can see that Steve is always an outlier in comparison to the regular SAIDs. And it was the same for not only for the temperature that I am showing you here, the densities were lower than the typical SAIDs, and the velocities were definitely faster than what we were observing. So Steve is actually the optical signature of an extreme SAID. It's not the optical signature only of an SAID, but you have to have an extreme SAID for this to happen. So I was telling you earlier, we saw that downward field line current that will indicate particles moving in the other direction, particles moving from the ionosphere to the magnetosphere. So we needed to know if any particle precipitation was occurring. And for that, we use a satellite that measured particle precipitation. This is POST-17. This is an event that happened in 2008. This is 2008, March 28th. And we have 2 of those white light cameras that I mentioned at the beginning. This is higher latitudes and this is lower latitudes than this, so they are connected. These are the 2 of them are in Canada. So at higher latitudes within the auroral oval, you see all that luminosity, all those structure happening. The aurora is very active, and then while the aurora is clearly very active, saturated even at this time, we start seeing Steve in the equatorward portion of the oval. This is in the middle of this camera over here. It goes across the field of view of the camera. It gets structure, which is not something that is very unusual for Steve. This happens relatively commonly. And then at the time where the POST satellite crosses the structure, it gets a little bit fainter. In the video is much better, and then it goes away. So let's look at what POST was telling us, what the particle measurements from POST were telling us. So what we have here is particle fluxes. We have protons in the left, electrons in the right. And the green line corresponds to the time where the satellite crosses Steve. We have 2 types of populations that are being able to measure by POST. We're going to have the trap population, that is going to be the black line here. 90-degree pitch angle indicates that the particles are being trapped, and the 0-degree pitch angle, the blue line, are the precipitating particles. So we're going to look at the blue line, and if there are any changes in the fluxes, any increases in the fluxes, that means that the satellite is measuring all those particles raining down into the atmosphere. So if we look at the protons, you can see that there is no increase in the blue line for any of the energy channels that we're able to measure with POST satellite. That means no proton precipitation is involved in this process. When we look at the electrons, the situation is very similar. In blue, again, we have the precipitating population. We see that there is no increase in those fluxes for any of the 3 first energy channels. The 4th energy channel, however, has an increase, a clear increase. I have always wanted for someone to yell at the end of the room saying, then it's particle precipitation. And I say, no, not yet. We need to satisfy a requirement for the luminosity that we observe in the night sky to be related to the precipitating particles. Yes, there are electrons precipitating in these very low energy channels, but for these electrons to create a visible structure, there is a threshold. The integrated energy fluxes need to be more than 1 erg per centimeter squared per second. And when we look at that quantity, this is integrated energy flux as a function of time. Green line is when we cross Steve. You can see, even if you look at the scale, this is orders of magnitude smaller than what we need to produce this optical structure. So yes, we do have very low energy precipitating electrons, but those electrons are not responsible for the optical emission that we are seeing in the night sky. Therefore, we propose that actually Steve is not produced by particle precipitation like aurora. Steve is not aurora, but it's a phenomena produced within the ionosphere. It's locally produced in the ionosphere. So if you want to call it Steve aurora, no, don't call it Steve aurora, just Steve. And that was further, and this is the last piece of information, that was further studied with an instrument that is a spectrograph. This is a very high sensitive imaging spectrograph that emissions between 400 to 800 nanometer emissions. And with this, we were able to observe not only Steve, but also the picket fence. So what we did here is, and this was a brilliant analysis, we compare the luminosity first within the picket fence and then compare it with the background power and equator. I want you to remember that the blue line is going to be the most interesting one for the analysis. So what we have here is similar to what you saw for that atomic oxygen spectrum. We have luminosity as a function of wavelength. And when we look at all the three curves, if we start at the lower wavelength, you can see that all these three curves more or less move together until we get to the 5577 nanometer emission. That is this one over here, that's a green line. And then the three of them move together again. So the picket fence is actually pure green line emission. And this was very puzzling because we have no emission in the red line. And usually when we have particle precipitation, you get the green and you also get a little bit of the red, and that was not happening here. So the spectrum was super, super pure. You're going to hear that many people argue whether or not the picket fence is produced by precipitation or something more locally in the ionosphere, and that's a big, big controversy. Similar again, we did the same for Steve, luminosity within Steve, luminosity power, and equator. And again, I want you to focus on the blue line that is going to indicate Steve luminosity. And we have exactly the same plot, luminosity as a function of wavelength. And if you start looking at this, the blue line is always more elevated luminosity than the luminosity power in all of the wavelengths. And it has luminosity at all wavelengths. This is not a discrete spectrum. This is a continuum spectrum in a very wide wavelength range. So Steve is not discrete emission like we see in the aurora. Steve is a continuum emission, and that's why when we see it in the night sky, when we see it in the photographer's data, it looks so white because it's a continuum emission. And that was completely different to what we observed for the aurora. So Steve is definitely not aurora. A little bit of the background when we look at the geomagnetic conditions for Steve. Steve is typically observed during relatively active conditions, from small storms to large storm. We have seen it you might be familiar with the St. Patrick Day storm of 2015. We had Steve there. We didn't see Steve last year in some of those strong storms that we had, but we have seen Steve in comparable strong storms. And what it was very interesting, Steve is always associated with a substorm that is indicated by the AL index. So we compare with regular substorms. The substorm of Steve appeared to be longer, so we might be able to inject more energy from the magnetotail towards the inner magnetosphere to not only modulate the ring current, but also modulate the reaction of the ionosphere. And that's something that we're still working on. So in summary, and this is a bit of what I told you, a bit of what we know, we have several Steve characteristics. Steve is associated with an extreme subauroral ion drift. Steve is not produced by particle precipitation like the aurora. The origin of the picket fence is still under intense debate. Most Steve events occur during storm and substorm conditions. Steve is very narrow, but very wide in longitude. It covers many of those hours that in that clock that I was showing. Steve altitude is between 130 and 170 kilometers, while the picket fence is a little bit lower, 95 and 150. and Steve generation mechanism is still an open question. When we look at some of the unusual observation of Steve, we have seen transformations of something that we call a star arc into Steve. That's still very unknown. We have seen SAIDs that have reached 10 kilometers per second, so 10 times faster than what we typically expect. Quiet time Steve have been also reported when we don't have storms up or substorm. And during this quiet time, the oval appears to be a very high latitude, something that we didn't expect. And there are many, many open questions on Steve, on the picket fence, and on the suborbital ionosphere that we are still working on. So this topic is full of opportunity for discovery. Before I finish here, I just want to tell you a message. One of the best advice that I have gotten when I was a student from one of my professors, and something that I have seen, especially in the Alaje community, in the inter-Alaje community, and is that cohesiveness that I see with the students. And I love that you are all so united, because in many years, you are going to be the ones reviewing each other's paper, reviewing each other's proposal, and shaping the field, not only Latin America, but also worldwide. So be kind to your colleagues, support each other, and keep doing what you have been doing. Thank you so much.
Thank you very much, Bea, for your talk and your final advice. Um, and I don't know if you have a question in YouTube or here in Zoom. Why I have a question there about Steve. Does Steve have a seasonal preference, maybe? Mm.
It does. So well, when we look at all the optical data that we have in the field, we saw that Steve has a preference for the equinoxes, so spring or autumn. But one of the things that we know is actually substorms are more common during the equinoxes, and that effect is called the Russell-McFerron effect. So if Steve needs that energy from the substorm to occur, it makes sense that it's seasonal. So over there, kind of, we understand why this is happening.
Okay. Yes. So, well, is a topological reason the seasonality in this case, right?
I think it's mainly a magnetospheric energy input. The seasonality is given by the magnetosphere in this case, more than the ionosphere. Although while we think that all the injections that are happening in the magnetotail are influencing the response on the ionosphere, I don't think we have done the one-to-one physics to say, well, we have all these injections in the tail, the suborbital region is changing this much. I feel like we're still missing a bit of the modeling there to understand what's the physics that is playing a role here. So yes to the magnetospheric, but kind of a bit of hand waving of how the ionosphere is responding.
Okay, thanks. We have another question in YouTube for Jamie. Uh, no, sorry. Has these colors always appear red and white?
It's always like kind of purple, or in English, the word is mauve. That is that kind of magenta looking color. But when you look at it with your bare eyes, for what the photographers have tell us, it looks very white. And the red is because the red emission in comparison to the background is slightly brighter. So it's slightly brighter in the red. So the answer to that is yes, you will normally see a bit of white and a bit of red more predominant in Steve production.
Thanks. I don't know in Zoom we have questions. So Thank you very much, Bea, for the talk today. And the people of Interalaje, see you in the next Interalaje series. And would like to invite you for our next activity is a workshop lead for Giorgio Picanso, and the workshop during 3 days. So we were very happy share the Giorgio works. So see you in the next Interalaje activity, and thank you again, Bea.
Thank you so much. Bye, everyone.
Yeah, thank you very much.